Most people have heard that atoms are mostly empty space. You've probably heard it 1,000 times. Atoms are 99.9% empty, people say, and then they draw this little picture with a nucleus in the middle and some electrons whizzing around like planets. And they show this giant empty space and say, see, mostly nothing. But here's the thing, and this is important, that's not really what's happening at all. The word empty is the problem. It gives you a completely wrong picture of reality. Let me think about this carefully. What do we actually mean by empty space? If I have a volume of space and there's nothing in it, nothing at all, what's there? Well, you can't even ask that question sensibly because empty implies nothing is there. But in an atom, the space isn't empty. It's filled with something very different from what you might imagine. See the classical picture we all learned, the Bohr model with electrons orbiting like little planets. That picture is fundamentally wrong. It's been wrong for about 100 years, but we keep teaching it because it's easy to draw on a blackboard. And that's the source of all the confusion. When you imagine an electron as a little ball and the nucleus as another little ball, then yes, the space between them looks empty. But electrons aren't little balls. Here's what's actually happening. An electron is not a particle in the classical sense. It's a wave. Or rather, it's something that behaves as both a wave and a particle, depending on how you look at it. When an electron is bound to an atom, just sitting there quietly without you trying to observe its exact position, it acts like a wave. And this wave isn't localized to one point. It's spread out over a region of space. We call this the electron cloud, or the orbital. The electron is literally filling the space around the nucleus with a kind of probability density. It's not that the electron is sometimes here and sometimes there. It's that there's a distributed pattern of electron density. Let me give you an analogy. Imagine a drum head, and you pluck it. You get a vibration pattern, a standing wave. The drum doesn't have empty space in it. The whole surface is vibrating in a specific pattern. Now imagine that pattern is three-dimensional, and that's what an electron is doing in an atom. The electron isn't a point particle bouncing around. It's a three-dimensional standing wave pattern around the nucleus. Different orbitals have different shapes. S orbitals are spherical, p orbitals are dumbbell-shaped, and so on. Each shape represents a different standing wave pattern. Now this is crucial. These electron waves don't fill the atom uniformly. They're more dense in some places than others. That density distribution, represented by the square of the wave function, as mathematicians say, tells you where you're most likely to find the electron if you try to measure its position. But when it's not being measured, when it's just existing quietly in the atom, it's not localized, it's smeared out. It fills the entire atom with this probability cloud. So what do we mean when we say there's space between the nucleus and the electron? We mean there's a region where the nucleus is very small, incredibly small, a femtometer or so across, and the electron cloud is much larger. But that larger region isn't empty. It's completely filled with electron cloud. There's no empty space in the way we usually think about empty. There's electron density throughout. Now, here's where it gets really interesting. You might ask, okay, so the electron is this cloud, but what about atoms bonded together? What's between atoms? And this is the key to understanding why matter feels solid, even though atoms are mostly composed of low-density electron clouds. When two atoms get close to each other, their electron clouds start interacting. And here's something wonderful about quantum mechanics. Two electrons can't be in exactly the same quantum state. This is called the Pauli Exclusion Principle, discovered by Wolfgang Pauli. It's one of the most important principles in nature because it's responsible for the structure of the periodic table, and it's also responsible for why matter feels solid. When the electron clouds of two atoms start to overlap, what happens? The electrons want to lower their energy by occupying the lowest available energy states, right? But they can't all pile into the same state. The Pauli principle says no. No two electrons can have the same set of quantum numbers. So when you try to push two atoms together, the electrons that would naturally fall into the lowest energy states around the nuclei find that those states are occupied. They're forced into higher, more energetic states. And to force them into those higher states takes energy. You have to do work to push the atoms together. And that's not just a small force. That's a huge force on the atomic scale. That's the force that keeps atoms from passing through each other. That's the force that makes your finger feel solid when you touch a table. It's not like your finger is resting on something solid. It's that the electron clouds are pushing against each other with tremendous force because of the Pauli principle. There's also another effect happening, electrostatic repulsion. The electron clouds are negatively charged, and like charges repel. So you've got both the Pauli exclusion pushing electrons into higher energy states and electromagnetic forces repelling the electron clouds from each other. Both of these things combine to create an enormous resistance to atoms passing through each other. But here's the thing that makes this interesting. The resistance comes not from atoms being solid, but from forces, from quantum mechanical forces and electromagnetic forces. The solidity you feel is not because you're touching something hard and substantial, it's because you're experiencing the repulsion of electron clouds. It's a force field, in a sense. Now, I want to address something that bothers a lot of people. They say, well, if atoms are mostly empty, couldn't I pass my hand through a table? And the answer is no. The Pauli principle prevents it, and not in a way that you could overcome with effort. It's not like pushing against a spring. It's more fundamental than that. The energy required to force atoms to interpenetrate is essentially infinite on the scale of human experience. Let me tell you about a beautiful experiment that showed this. In the 1910s, Ernest Rutherford fired alpha particles at thin gold foil. Most of them went straight through. Some of them bounced back. And this was shocking. If atoms were solid, like little spheres, most of the alpha particles should have hit nuclei and bounced back. But they didn't. Most went straight through empty space. This told us that atoms really are mostly empty, in the sense that nuclei are incredibly small, and you can fire particles through and miss them. But here's the key insight from that experiment. The alpha particles went through the electron clouds. The electron clouds slowed them down and deflected them, but they still got through because the nucleus is so tiny that most particles just miss it. The electron cloud doesn't stop the alpha particles. It just weakly deflects them because the alpha particles are moving so fast that they don't spend much time being deflected. Now, let's think about the actual structure. The nucleus of an atom is about 100,000 times smaller in diameter than the whole atom. If you imagine scaling up the atom to be as large as a stadium, the nucleus would be the size of a marble sitting in the center. The electron cloud would fill the whole stadium. But the stadium isn't empty. It's filled with this probability distribution of electron density. And that's what prevents atoms from collapsing, and that's what makes matter feel solid. So where does that leave us with the idea of empty space between atoms? Well, I'd say the term is deeply misleading. When we say atoms are mostly empty space, what we really mean is that the mass of an atom is concentrated in a tiny nucleus, while the electron cloud is spread out over a much larger volume at lower density. But that doesn't mean the space is empty. The space is filled with electron clouds. And here's something else that's important. Space is never really empty anyway, even outside of atoms. According to quantum field theory, the most accurate theory we have for describing the behavior of matter and forces, empty space is fizzing with virtual particles constantly popping into existence and disappearing. There's the Higgs field, there are other quantum fields, and there are fluctuations happening all the time. So truly empty space doesn't really exist. But let me bring this back to atoms and molecules, because that's where the rubber meets the road in everyday experience. When you have two atoms that are bonded together, say in a hydrogen molecule, two hydrogen atoms bonded together, what's between them? Well, there's an overlap of electron clouds. The electron clouds from the two atoms interpenetrate, and in the region between the nuclei, there's high electron density. The electrons from both atoms occupy that region, contributing to a negative charge density that attracts both positive nuclei holding the molecule together. There's no empty space in the bond. It's filled with electron density that's responsible for the bonding. Now you might ask, isn't that what we mean by a chemical bond? Exactly. A chemical bond is not some little stick holding atoms together. It's a region of high electron density between nuclei that attracts them together and holds them in place. The overlap of electron clouds is what creates the bond. And when atoms are not bonded, when they're just next to each other, the electron clouds don't overlap much, but they still interact. They repel each other. The electrons in one atom repel the electrons in the neighboring atom. The nuclei in one atom attract the electrons in the neighboring atom, but those electrons can't get too close because of the Pauli principle and the repulsion of the first atom's own electron clouds. So all these forces balance out to some equilibrium distance. That equilibrium distance is why atoms have a definite size. That's why matter has density and volume. Think about it this way. If atoms were truly hollow spheres with tiny nuclei in the center, what would determine the size of the atom? There'd be nothing to set a distance scale. But electrons are waves spread throughout the atom, and the Pauli principle and electrostatic forces create a balance that gives atoms a definite radius. That's beautiful. That's how nature really works. So when someone tells you atoms are mostly empty space, what they really mean, or what they should mean, is the mass of atoms is concentrated in tiny nuclei, while the volume is occupied by electron clouds. It's not empty in the way that the word empty usually implies. It's filled with electron probability density, and this has profound implications for understanding everything. It explains why matter has the properties it does. It explains why some substances are hard and brittle, while others are soft and malleable. It explains chemical reactions where atoms rearrange their electron configurations to lower their energy. It explains how life is possible, how molecules can form that are stable and complex enough to carry information and drive metabolism. All of that emerges from the same fundamental principle. Electrons are waves, they obey the Pauli Exclusion Principle, and electromagnetic forces act between them and nuclei. That's it. That's the foundation. No empty space, no solid little spheres, just quantum mechanics at work. You know what I find remarkable? That nature at its foundation is not made of things, it's made of patterns. The electrons are patterns of probability. The atoms are patterns of these electron waves around nuclei. Molecules are patterns of overlapping electron clouds. And the whole universe, as far as we can tell, is made of these patterns interacting according to mathematical rules. And we can describe these patterns. We can solve Schrödinger's equation, or approximate it, which is what we usually do because the exact solution is too complicated. And we can predict the shapes of electron orbitals, the energies of atoms, the properties of molecules. We can predict whether a molecule will be stable or reactive. We can design new materials with desired properties, all from understanding that electrons are waves, not little balls, and that they obey quantum mechanical rules. So the next time someone tells you that matter is mostly empty space, think about what they really mean. They don't mean you could push your hand through a table. They don't mean the universe is mostly nothing. They mean that the way matter is structured, with density concentrated in nuclei and spread out in electron clouds, is not what our intuition might suggest from everyday experience. Nature is subtle. Nature is almost nothing like the simple models we learned first. And that's the beauty of physics. The closer you look, the more there is to see, the more you understand, the more wonderful it becomes. The idea that you can't walk through a wall because of the Pauli Exclusion Principle, because electrons can't be in the same quantum state, because of forces arising from the wave nature of matter, that's profound. That's the kind of thing that makes you realize how much there is we don't understand and how much more we have to discover about how the world really works. When you understand atoms at this level, you start seeing the world differently. You see that solidity isn't a fundamental property of matter. It's an emergent property that comes from quantum mechanics. You realize that chemistry isn't magic. It's just atoms rearranging their electron clouds to find lower energy configurations. You understand that life itself is chemistry at a higher level of organization, and it all grows out of these same basic quantum mechanical principles. And that's worth thinking about. That's worth understanding, because when you understand the foundation, you start to see how everything connects. You see that physics, chemistry, biology, they're not separate subjects. They're different perspectives on the same underlying reality, described by quantum mechanics and electromagnetic forces. So the next time you touch something and it feels solid, remember, you're not touching hard matter. You're feeling the repulsion of electron clouds. You're experiencing the Pauli Exclusion Principle in action. You're touching a manifestation of quantum mechanics, and that's far more interesting than hard stuff, I think.